Hello, and welcome to this vodcast, part of the topic 5, electricity and magnetism, on combining resistors, although I'd say it's more accurately described as solving circuits and combining resistors. To justify that statement, what do I mean by solving a circuit? Solving a circuit is a lot like solving an equation. If you can solve an equation, you are able to take an equation with some variables that are known and some variables that are unknown and use your knowledge in order to discover what all of the variables are, to know all of the variables. It's a very similar concept of a circuit. You'll be given a circuit about which some information is known and you have to work out what you don't know. The information you might be given or you might be asked to discover is generally the resistance of different parts of the circuit, the current at different points in the circuit, or the potential difference between any 2 points in the circuit, or things that you can easily calculate from that, such as the power. The tools that you have, fundamentally the most important one is the equation for resistance V equals IR. As you will see, applying that enables you to solve most fairly simple circuits. P equals VI enables you to incorporate the power information, either if you want to work that out or if you are given that. There are rules for combining components, particularly for combining resistors, which we're going to look at soon. Rules for combining other components, such as power supplies, we'll look at a bit later. All of this can be brought together under a set of rules called Kirchhoff's laws. Kirchhoff's laws for circuit analysis, current and voltage. But we'll build up to those. We'll start with a more simpler situation, which is just combining resistance. Just to review, what I think you should already know, we have two different types of circuits, series circuits and parallel circuits. Series circuits have no junctions. There is just one continuous loop of current, and therefore the same current exists in all parts of the circuit. Whatever current is entering a part of the circuit is also leaving a part of the circuit, and therefore the current is the same everywhere. However, the potential across the different components adds together. That's as opposed to a parallel circuit, which does have junctions, an even number of them. The currents add together and the same potential exists across each branch. Now those statements might be a little bit confusing, so let's just break that down a little bit more. Just looking at a series circuit, since there are no junctions, any current entering any part of the circuit must be the same. I1 equals I2 plus I3. I've written A's there for the ammeter, but the current I1 must equal I2, must equal I3. The potential differences, however, add, because the total potential across both resistors must be the same as the potential across the supply. All the energy that is supplied has to be used. So therefore V1 must equal V2 plus V3. Similarly, looking at parallel circuits, the currents add together, because any current entering a point in the circuit must leave the same circuit. So at the point here, this junction here, current I1, as measured by the ammeter A1, must be entering, and then that must equal these two things leaving. So these two currents are leaving this point in the junction. What enters must go out, so I1 must equal I2, as measured by A2, and I3, as measured by A3. And then, at this junction here, those two will recombine. So I2 plus I3 at A2 and A3 must equal I4, and I4 must equal I1. So they add. Whereas the potential must be the same. The energy across this branch must be the same as the energy across this branch, because that energy is provided by the supply. So for any charge carrier carrying energy, it can follow one of two different loops. It can go around here or it can go around here. But no matter what route it takes, it gets the same amount of energy, therefore it must lose the same amount of energy. Therefore, for every unit of charge that passes, the same amount of energy must be lost across these two resistors. Therefore, V1, V2, and V3 must be the same. So, how do we actually use this information to help solve the circuit? Well, when it comes to this, one of the things we can do is we can combine resistors. We basically take a circuit and say, what is a simple circuit with just one resistor that would give the same resistance as the combination of series, parallel, or more complicated situations, both that we have. In other words, if I have 20 ohm resistors and I put them in series, what one resistor could I replace them with that would have the same effect, that would produce the same current if we have the same potential difference across our supply? Similarly here, take those two 20 ohm resistors and arrange them in parallel, same supply. What would the current now be? What single resistor could we replace these resistors with which would give us the same current? Let's look in more detail at series. Well, for a series resistor, we can set up a series of ammeters and voltmeters, arranged like we've just seen. We know that V equals IR, therefore we know that R equals V divided by I. Therefore, the total resistance, which is what this one is here, must equal the potential difference across it divided by the current through it. We know that this V1 equals V2 plus V3. We just saw that. So V1 over I1 equals V2 plus V3 over I1. Separate those out. V2 over I1 plus V3 over I1. But now V2 over I1 and V3 over I1 are the resistance of R1, this resistor here, and R2 there. So the total resistance equals R1 plus R2. And that is the rule for combining resistors. If you have two or more resistors in series, then the total resistance is R1 plus R2. Now looking at parallel resistors, we can set up the same arrangements of ammeters and voltmeters so we can see what's going on in the system. And now we can rearrange V equals IR in a different way to give us I equals V divided by R. We know that for a parallel circuit, the current I1, as measured at A1 here, equals I2 plus I3, as measured at these two ammeters. That's the rule for a parallel circuit. So I1 is V1 divided by R, just this equation here. So the current through here equals V1 divided by whatever this resistance is. And that, therefore, substituting means that V2 over R1, which is the current through here, and V3 over R2, which is the current through here, must also add together to give this overall current. I1 plus equals I2 plus I3, this current equals that current plus that current. So, in other words, and just to remind you, also, since this is a parallel circuit, all these potential differences are actually the same. V1, V2, and V3, that should say, are identical. Therefore, I over 1 over R equals 1 over R1 plus 1 over R2. So that's the rule for a parallel resistor. 1 over the total resistance equals 1 over the first resistance plus 1 over the second resistance. And if we had further resistors in parallel, you could add those onto the end. Going back to our question then, if we have these 20 ohm resistors, what happens? Well, in the case of a series circuit, we use that equation. In the case of a parallel circuit, we use the second equation. Series is easy, 20 plus 20 equals 40. Again, logically this makes sense. If you consider resistance to be the degree of difficulty current has in passing through components, if you add those two components together in length, it has to pass through both of them, therefore it will be twice as difficult. Parallel is a little bit more tricky. 1 over R, the total resistance, equals 1 over 20 plus 1 over 20. So 1 over R equals 2 over 20. Common mistake, people go, oh, that's it, R equals 1/10. No, 1 over R equals 2 over 20. So R equals 20 over 2. So R equals 10 ohms. Again, that makes sense from a sort of physics point of view, so to speak. If you compare one resistor, by putting another resistor across it, we're making it easier for the electricity to flow. It's easier for the current to pass through two of these resistors in parallel than it is any one resistor. It has more paths, it has more options, it has more choices. Don't anthropomorphize, but that's kind of what we're saying. In fact, the rule is that whenever you add a resistor, the combined resistor, whenever you add a resistor in parallel, the combined resistance must be less than the smallest resistance. If you have identical resistors, such as we have here, then it's very simple because the combined resistance for two identical resistors in parallel will always be half any one resistor. So, What happens if you have more complicated circuits, such as this one? I'm not giving the whole circuit, I'm just giving like a section here, several resistors in series and parallel. Well, again, you just want to boil it down to, simplify it down to one resistor. And that word simplification is what we do. So we just take it in steps. We have here two series resistors and two series resistors. Like we see here, we can apply the series resistance equation to combine them. Now we have two parallel resistors here, and we can use the parallel equation to combine them. And now we have two series resistors again, so we can use the series resistance equation to combine them, which is what we have here. So to summarize, there are series circuits, there are parallel circuits. Remember or see what you have, apply the appropriate equations, and if you need to, if there's a slightly more complicated circuit, then apply the process of simplification step by step, which can take a long time, but it gives you the right answer in the end to find out the overall resistance. It's a little bit more complicated than that often in practice, because generally you're not going to be given simple resistances. You have to work them out from other information. So it would probably be a good idea to do some worked examples, but this video is long enough, so we'll look at doing that in another video. Here are the data booklet sections that we've used. So R equals V over I, and the R total equals R1 plus R2 plus whatever for series, and 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc. For parallel. Be aware that, you might well have more than one series resistor at a time, because that's really easy, but I don't think I've ever seen in an IB question more than two resistors in parallel together. Thank you very much. I hope that was